This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas.
I want you to put yourself in a very specific, highly uncomfortable situation for a moment.
Oh, setting the scene right away.
Yeah, exactly. So you are sitting in a completely open wooden boat.
Mm-hmm.
There's no cabin structure.
None at all.
Right. There's no below-deck galley to retreat to, no reinforced glass windows separating you from the environment, and absolutely no modern navigation instruments glowing on some console.
They're just totally exposed.
Completely.
Yeah.
You're exposed to the elements in a way that, modern travelers rarely experience. Above you, the sky isn't just cloudy, it's this bruised, unrelenting gray mass that just seems to, press down on the water.
Yeah, that classic North Atlantic look.
Exactly, because all around you is the North Atlantic.
Exactly.
And this isn't, the gentle rolling ocean of a summer cruise. This is freezing, chaotic, turbulent water.
The kind that really tests a ship.
Oh, absolutely. And you are currently looking up, actually craning your neck up past the mast at a sheer wall of water.
Terrible.
A 14-foot wave is just bearing down on you, carrying, the entire accumulated kinetic energy of a mid-ocean storm.
And the physics of a wave that size are just, they're terrifying when you consider what you're sitting in.
Right.
Because it's not just the vertical height that poses a threat, right? It's the sheer crushing mass of that water.
I mean, water's incredibly heavy.
Yeah, exactly. A cubic meter of seawater weighs over a ton. So that wave represents, thousands of tons of localized force. And it sounds like a freight train of tearing ice and compressed air.
It's a wall of destruction.
Right. And if you are in almost any other ship built 1,000 years ago, like, say, a heavy merchant cog or one of those rigid, high-castled European vessels, that wave is basically a structural death sentence.
Because they just couldn't handle that kind of localized force, right?
Exactly. The standard maritime engineering of the era, it relied entirely on rigidity to fight the ocean.
Like a floating fortress.
Right, a fortress. But when thousands of tons of water hit a rigid, thick timber frame, the energy, it has nowhere to go. The frame takes the full brunt of the shock.
And then it just breaks.
Yeah, the timbers splinter, the structural ribs fracture, and the hull catastrophically fails.
Yeah.
And then, you're plunged into water so cold that the shock induces an involuntary gasp reflex.
Oh, wow.
Yeah, you end up filling your lungs with seawater before you even consciously register the temperature.
That is incredibly grim.
Yeah.
But the scenario changes entirely because of the specific vessel you are in this thought experiment.
Right, the crucial detail.
Because you are not fighting the ocean in a rigid wooden fortress. You're sitting in what we're going to argue today is the most perfectly realized, brilliantly engineered piece of maritime technology of the medieval period.
You are in a Viking ship.
Yes.
And when that 14-foot wall of water collapses onto your position, the wood beneath you does something incredibly counterintuitive for a heavy medieval structure.
It doesn't shatter.
Exactly. It doesn't shatter. It flexes. The entire hull twists and bends, absorbing that colossal kinetic energy of the ocean swell. It literally rolls with the violence and lifts you up and over the crest completely intact.
Which is just, it's wild to think about. Welcome to today's deep dive. We are setting sail into the world of the Norsemen, but we are actively abandoning those tired, caricatured Hollywood tropes, right?
We're leaving the myths behind.
Yeah, we aren't talking about unwashed barbarians and horned helmets, which, by the way, is a detail totally invented by 19th century opera costume designers.
One of the most persistent myths out there.
It really is. So our mission today is to deconstruct an ultimate medieval machine. We are examining an engineering, industrial, and maritime revolution that, it fundamentally altered global history.
Because it wasn't just about raiding.
Exactly. We're looking at how a specific understanding of nature allowed a decentralized culture to project power, establish trade routes spanning from, the markets of the Abbasid Caliphate all the way to the coastlines of North America.
Which is a staggering geographic spread.
It really is. And to navigate the open ocean centuries before the rest of Europe even felt comfortable leaving the sight of land.
It's a profound story, of human adaptation and early industrialization. To really understand the scope of this achievement, We have to look past the mythology. We have to focus on the mechanics, the economics, and the physical reality of how these vessels were actually constructed and operated.
And we have an incredible array of data to help us unpack this today. We've got a great stack of sources guiding our journey. We're synthesizing a New York Times report on a really daring experimental archaeology project, a detailed woodworking breakdown from Hurstwick.
Which is fantastic for the technical details.
Oh, absolutely. Along with historical overviews from Freysta and the Royal Museum's Greenwich, and some great archaeological class notes from Fiveable.
It's a very comprehensive set of data.
Yeah, it really covers all the bases. So, okay, let's unpack this. To understand how a society manages to cross an ocean and survive a 14-foot swell, we can't start at the shipyard, right? We have to start much smaller and, well, much further inland. We have to understand a single oak tree.
Yeah, the engineering genius of the Viking ship really begins at the absolute micro level. I mean, we're talking about the molecular structure of the wood itself.
Right.
The construction process didn't begin with clear-cutting a forest. It began with highly targeted, deliberate selection. A master shipwright would scour the landscape for a very specific type of tree.
So they weren't just grabbing whatever was closest.
Not at all. And they weren't looking for the tallest, straightest oak in the middle of some dense, sheltered grove either. They were often looking for trees that grew on hillsides or in really challenging, windy coastal environments.
Which, I mean, that seems like it would produce a compromised piece of timber, right? Because if trees growing on a steep incline, constantly battered by wind from one direction, it's not going to grow symmetrically.
Yes.
The trunk is going to be under constant tension on one side and compression on the other. That sounds like a flaw.
But that asymmetrical growth is precisely the point. The shipwrights were essentially reading the life history of the tree.
Oh, interesting.
Yeah, when an oak grows on a slope, fighting gravity and fighting the wind, the growth rings don't form those perfect concentric circles radiating from the exact center of the trunk.
Like you see in, a typical tree stump.
Right. Instead, the tree reinforces itself. It packs its growth rings incredibly tightly together on the side that's bearing the structural load.
So it gets denser.
Exactly. This means that one specific section of the trunk becomes exceptionally dense and highly stressed. And the shipwrights intentionally targeted this dense asymmetrical timber because it inherently possessed the exact structural properties they needed to combat the extreme forces of the open ocean.
So they find this battle-hardened oak, they fell it, and then they have to turn it into planks. And this is where the manufacturing process just radically diverges from standard European shipbuilding.
A total departure.
Right, because the traditional method for making a plank is pretty simple. You take a giant saw, you lay the log down, and you slice it into long, flat boards.
Right, which makes logical sense to us today.
Yeah, it's how we build houses.
Yeah.
But the Norse shipwrights completely rejected the saw for plank making. They use a technique called riving.
Riving is, well, it's a process of splitting the wood rather than cutting it, and it is incredibly painstaking. It requires a profound understanding of the material's internal architecture.
Because you can't just hack at it.
No. A master woodsmith scores the face of the oak log exactly along the line where they intend to force a split. Then, they systematically drive a series of iron or wooden wedges directly into the end grain.
So they're prying it apart.
Yes, as the split begins to open, they drive more wedges down the side of the trunk, forcing the wood to separate along its natural internal pathways. So they split the log entirely in half. Then they take those halves and split them into quarters. And they continue this geometric division, splitting quarters into eighths, and sometimes even sixteenths, depending on the diameter of the log.
Let's visualize why this method is structurally superior to sawing. Because on the surface, it sounds like an incredibly labor-intensive way to get a plank that you could have just cut in a fraction of the time.
It does seem inefficient at first glance.
Yeah, so think about the mechanical properties of a piece of string cheese.
Okay, string cheese.
Hear me out. If you lay a stick of string cheese on a cutting board, take a knife, and slice it crossways into little medallions, those individual pieces have no structural integrity.
Right, they just fall apart.
Exactly, because you've taken a blade and severed all the internal longitudinal fibers. You can snap those medallions in half with almost zero effort. But if you peel the string cheese, if you grip the end and pull it apart, forcing it to separate along its natural continuous fiber.
And it holds together.
Right. Those individual strings are remarkably resilient. You can pull on them, twist them, and they resist breaking. Riving wood operates on the exact same mechanical principle.
That analogy perfectly highlights the core vulnerability of the saw. A saw is essentially a destructive tool.
Because it doesn't care about the grain.
Exactly. It cares nothing for the internal architecture of the tree. As the saw blade moves blindly through the log, it inevitably slices diagonally across the natural wood fibers, which creates thousands of microscopic weak points.
So it's already compromised before it even hits the water.
Yes. When a sawn plank is subjected to the immense lateral pressure of an ocean wave, it is highly prone to shearing or snapping right along those severed fiber lines.
But the riven plank retains all its internal strength.
It retains absolute continuity. By splitting the wood with wedges, the craftsman forces the separation to follow the natural grain from one end of the log to the exact opposite end.
The fibers run the entire length.
Right. The cellulose fibers remain completely intact and unbroken. And this single technological choice allowed Viking shipwrights to produce planks that were exponentially stronger than the timber used by their contemporaries.
It's just a brilliant observation of nature.
It really is. Because the riven wood possessed such immense inherent strength, they didn't need to make the planks thick and heavy to ensure they wouldn't break. They could make them astonishingly thin, sometimes less than an inch thick, and incredibly lightweight without sacrificing an ounce of durability.
And the sensory details of this process, well, they're vivid. We're talking about a workshop environment where the master craftsman is actively discarding the soft outer sapwood and the weak inner pith of the tree.
Right, getting rid of the dead weight.
Yeah, they're isolating only that incredibly dense, tightly ringed wedge of heartwood. And then comes the shaping. And they don't use planes or sanders. They use specialized axes and a tool called a froe, which basically allows them to leverage and steer the split in real time.
Applying precise pressure to manipulate the wood's properties as it separates.
Exactly.
And the refinement stage is where the true artistry emerges. Once the rough wedge is isolated, it is locked into a heavy wooden vise called a shave horse.
Which sounds very rustic.
It is, but highly effective. The craftsman sits straddling the bench, securing the wood with a foot-operated clamp, and goes to work with a draw knife.
Right.
This is a blade with two handles that is pulled toward the body. Historical accounts emphasize that this blade had to be maintained at a razor-sharp edge. The craftsman pulls the draw knife along the grain, shaving the dense oak down to its final paper-thin dimensions.
I can imagine that takes serious effort.
The physical exertion is immense. The accounts describe the heavy oak shavings literally flying through the air of the workshop as the plank is rapidly, violently refined into a flawless, continuous grain component.
So we have a stockpile of these exquisitely crafted, incredibly strong, remarkably thin oak planks. But obviously a pile of exceptional wood does not equal a seaworthy ship.
Right, you have to put them together.
Yeah. And the method used to assemble these components into a hull is arguably the most radical departure from standard naval architecture of the period.
We are talking about the clinker-built or lapstrake method, and to understand why this was revolutionary, you have to contrast it with the standard frame-first construction that dominated European, Mediterranean, and later global shipbuilding.
Because almost everyone else did it the other way around.
Exactly. In frame-first construction, you build the internal skeleton of the ship before anything else. You lay a heavy keel, you erect massive, rigid wooden ribs, and then you take your heavy sawn planks and nail them flush, edge to edge, onto the outside of that rigid skeleton to create the skin.
Right, which makes logical sense from an engineering standpoint. I mean, you build this strong supporting structure and then you attach the walls.
Sure.
But the Norse shipwrights essentially inverted that entire philosophy. They utilized a shell-first method. They lay the keel down as the spine, and then they immediately start attaching the planks. And they don't place them edge to edge, they overlap them.
Right. The overlapping is the key.
Yeah, each plank is laid so its lower edge slightly overlaps the upper edge of the plank beneath it. It mirrors the overlapping clapboard siding you would see on the exterior of a modern house.
Yeah, a lapstrake design.
And they secure this overlapping joint by driving an iron rivet through both planks, placing a metal washer, it's called a rove, on the inside, and hammering the rivet flat to lock it in place.
So they rivet the entire outer shell of the hull together before the internal structure is ever fully realized.
And I have to push back on the logic of this design, to be honest, because looking at it purely structurally, it sounds almost negligent.
Oh, how so?
Well, you are building an exoskeleton out of thin, flexible wood, riveting it together into a giant hollow eggshell, and only inserting the supporting ribs afterward, and shaping them to fit whatever curve the shell naturally assumed. It's like framing a house by nailing all the exterior siding together first, standing it upright, and just hoping you can wedge a load-bearing frame inside before the wind blows it down.
That is a great visual.
Right. Why adopt a construction method that relies entirely on the outer skin for its primary structural integrity?
Because you are assuming that rigidity equals strength.
Okay, true.
The clinker method is a deliberate rejection of rigidity. It is the pursuit of dynamic tension. If you build a heavy, rigid skeleton and nail thick planks to it, you are building a structure that is going to fight the ocean.
It's going to try to stand its ground against that 14-foot wave.
Exactly. But water is incompressible, and water always wins. The rigid wood is forced to absorb the entirety of that impact, leading to structural fatigue, cracking, and ultimately catastrophic failure. The Viking shipwrights understood that survival didn't come from resisting the force.
They came from dissipating it.
Yes, the hull is designed to yield. It is designed to move. Because they use those incredibly thin riven planks with the unbroken grain, and because those planks are only riveted together at the overlapping joints without a massive, restrictive internal skeleton locking them in place, the entire shell of the ship can twist, flex, and undulate.
So when a wave hits it, it just contorts.
Yes. When a massive wave strikes the bow, the clinker-built hull doesn't rigidly absorb the blow. It contorts. The energy of the impact travels down the length of the hull, dissipating as the overlapping planks shift and slide infinitesimally against each other. It absorbs the wave energy by moving with the water rather than opposing it.
Wow. And this philosophy of flexibility extended even to how they integrated what little internal framing they did use, right?
Yeah, it wasn't just the shell.
They didn't just aggressively nail every internal rib directly to the hull planks. They utilized lashings. They used highly durable materials like spruce roots or heavily treated ropes to literally tie the internal structural components to cleats that were carved directly into the inner surface of the hull planks.
Which is brilliant.
It really is. This meant the ribs in the hull weren't locked in a rigid, unforgiving bind. The components could actually shift, slide, and articulate independently under stress. It fundamentally changes how we should view the vessel.
It wasn't a static machine.
No, it was engineered to function like a massive, articulated living organism, adapting to the hydrodynamic pressures of the sea.
But, that level of articulation introduces a massive engineering problem.
Right, the water.
Exactly. If your entire hull is designed to constantly twist, flex, and shift, the overlapping joints between those planks are going to be subjected to immense movement.
They're going to slide against each other.
Yes. So how do you keep a constantly contorting, shifting puzzle of overlapping wood watertight in the middle of the North Atlantic?
The waterproofing methodology is, well, it's fascinating. And it's deeply rooted in the agricultural realities of the society. Because obviously they couldn't just seal it with modern silicon or rigid epoxies that would just crack the moment the hull flexed.
They needed something dynamic.
Exactly. They needed a sealant that was as dynamic as the ship itself, so they packed the overlapping gaps, which are called the strakes, with a dense fibrous composite. They used raw sheep's wool, dense mosses, and sometimes even cattle hair.
Very resourceful.
But they didn't just stuff it in dry. They saturated these biological fibers with thick rendered pine tar or tallow, which is purified animal fat.
And the chemistry of that mixture is highly effective. Pine tar is naturally water repellent and possesses antifungal properties that protect the wood from rot.
Which is crucial.
Right. And the lanolin, naturally present in the sheep's wool, adds another layer of water resistance. When you combine the structural matrix of the hair and wool with the highly viscous, sticky properties of the tar, you create a waterproof gasket that remains pliable even in freezing temperatures.
Never totally ardent.
Right. As the hull twists and the wooden planks shift, this fibrous, tarry gasket stretches and compresses, maintaining a watertight seal despite the constant kinetic movement of the ship.
It is an incredibly effective solution. Though I have to say, the sensory reality of living on that ship must have been totally overwhelming.
Oh, the smell must have been intense.
Right. The constant smell of rendered animal fat, raw wool, and hot pine tar baking in the sun, mixed with, the sweat of 50 rowers and the salt of the ocean.
Not for the faint of heart.
Definitely not. But the combination of all these micro-technologies, the continuous grain of the riven wood, the flexible dynamic tension of the clinker hull, the pliable waterproofing, it resulted in a vessel that possessed almost supernatural maritime capabilities.
Yeah, and the primary advantage of all this was speed and weight. Because the hull lacked heavy internal timbers and thick sawn planks, the overall displacement of the ship was astonishingly low.
Sat so lightly on the water.
Exactly. Under favorable wind conditions, historical estimates and modern reconstructions suggest these vessels could routinely hit speeds of 15 knots.
Which is roughly 28 kilometers per hour.
Right. And in the 9th century, achieving that speed on the open water was an absolute paradigm shift in human mobility.
But speed is only half the equation, right? Because the low weight and the specific geometry of the broad, flat-bottomed hull provided a tactical advantage that completely destabilized the geopolitical landscape of medieval Europe. And that is the shallow draft.
Yes, the shallow draft. Now, the draft is the vertical distance between the waterline and the bottom of the keel, essentially how deep the ship sits in the water.
How much water it needs to float.
Exactly. Most European merchant or military vessels of any significant size required deep water to operate safely. They were bound to established deep water harbors.
You couldn't just park them anywhere.
No, but a Viking longship, despite being 30 meters long and capable of crossing an open sea, might have a draft of less than half a meter when unladen.
Less than half a meter. That is a staggering metric. It fundamentally rewrites the rules of engagement, of trade, and exploration.
It changes everything.
A fleet of these massive, terrifying vessels could cross the turbulent North Sea, hit the coast of Francia or the British Isles, and instead of navigating to a fortified port, they could simply bypass the defenses entirely.
Just sail right past them.
Yeah, they could glide directly over shallow sandbars, sail miles up narrow, winding inland river systems, and beach the ships directly onto a sandy shore or a gravel bank without suffering any structural damage.
And the strategic implications of that cannot be overstated. I mean, inland monasteries, rural trading hubs, and population centers that were considered entirely safe from naval threats suddenly found entire fleets of warships unloading hundreds of men, quite literally in their backyard.
Right, nowhere was safe.
Exactly. The entire coastline, every river mouth, and every shallow estuary became a potential point of entry. The element of surprise was total.
And the whole geometry offered another crucial tactical advantage, too. Perfect symmetry.
Ah.
The bow and the stern were identical. They swept up into identical, graceful curves. In standard naval combat or river navigation, if you sail a massive ship up a narrow, hostile fjord and suddenly encounter an ambush or like an impassable obstacle, you have to execute a clumsy, time-consuming turn.
Which is incredibly dangerous.
Right. You have to pivot the entire mass of the ship in a confined space, exposing your broadside to attack.
But with a symmetrical clinker hull, turning around is completely unnecessary because the hull moves through the water with identical hydrodynamic efficiency in either direction. A trapped raiding party simply stopped rowing.
They didn't have to turn the boat at all.
Right. The rowers just turned around on their benches, faced the opposite direction, dipped their oars, and the ship seamlessly reversed course. They retreated at full speed without ever having to expose its flank or execute a dangerous pivot.
It is a terrifyingly efficient, highly mechanized approach to warfare. But the identical ends create a mechanical puzzle.
How do you steer it?
Exactly.
Yeah.
If the ship doesn't have a distinct flat back end like a transom, how do you mount a rudder to steer it?
Right, the steering mechanism is a brilliant piece of side-mounted engineering. They didn't utilize the central sternpost rudder that would become standard in later centuries.
Like we see on a galleon or something.
Exactly. They employed a massive, specialized steering oar mounted on the right-hand side of the ship near the rear. And this wasn't just an oar loosely tied to the side. It was secured to a heavily reinforced, rounded, wooden boss protruding from the hull.
It was a fixed mechanism.
Yes. The helmsman operated a tiller horizontal handle inserted into the top of the oar to rotate the massive blade in the water, leveraging hydrodynamics to steer the entire vessel.
And this design wasn't static. It was articulated. The mounting mechanism allowed the steering oar to be raised or lowered depending on the depth of the water, which of course was critical for a ship designed to operate in half a meter of water.
You can't have a giant rudder dragging on the bottom.
Right. If you are beaching the ship at high speed, you don't want your massive steering mechanism to slam into the gravel and snap. So the helmsman simply pulls a line, the oar pivots up out of the water, and the flat hull slides safely onto the sand.
And, the cultural legacy of that specific piece of engineering is still embedded in modern maritime language today.
Oh, this is one of my favorite details.
Because this crucial, delicate steering mechanism was mounted on the right side of the ship, A captain would always dock the ship with the left side against the pier.
To avoid crushing the steering oar against the dock.
Precisely. The left side became the port side. And the right side, the side with the steering oar, derives its modern name from the Old Norse term stýribor, which literally translates to steering board or steering side.
Starboard.
Starboard.
The entire global maritime community still uses a term derived from the specific mechanical layout of a 9th century clinker hull.
It's amazing.
Okay, so we have thoroughly analyzed the microengineering. We understand the cellular strength of the riven oak, the dynamic flex of the overlapping strakes, the chemical waterproofing, the shallow draft, and the side-mounted steering. We've constructed a masterpiece of a vessel.
We have.
But the Norse didn't just build a handful of exceptional boats. They built an armada that reshaped the world. We need to zoom out from the mechanics of a single hull and examine the sheer, staggering scale of the industrial complex required to sustain this maritime culture.
The scale is where the narrative really shifts from a story of skilled craftsmanship to a story of a highly organized, early industrial society.
It wasn't just a few guys in a shed.
No, historical estimates regarding the size of the Scandinavian fleet are sobering. Scholars like Professor John Vidar Sigurdsson from the University of Oslo suggest that during the height of the Viking Age, the combined regional fleets consisted of roughly 1,500 large ocean-going ships.
And to maintain a fleet of 1,500 wooden vessels, given, the attrition rate of storms, warfare, and just natural rot, the production output had to be immense.
They were constantly building.
Estimates from the sources suggest they were producing anywhere from 150 to 250 massive ships every single year. You do not casually produce 200 warships a year in a decentralized agrarian society without a profound level of logistical organization.
Absolutely not.
This required an intricate continent-spanning supply chain.
It necessitated a total mobilization of resources and labor. Just consider the iron alone. A single clinker-built ship requires thousands of iron rivets and rows.
Thousands per ship.
Yes. To build 200 ships a year, you need an unfathomable amount of iron. And they weren't just mining massive, convenient iron ore veins.
They had to use bog iron.
Exactly. They were heavily reliant on bought iron. And this is a complex metallurgical process where iron particles, dissolved in groundwater, are concentrated by bacteria in peat bogs.
It sounds so tedious.
It was. The Norse had to systematically locate these bogs, harvest the raw, muddy clumps of iron-rich material, dry it out, build massive clay smelting furnaces, burn immense amounts of charcoal just to reach the required temperatures, and extract the usable iron bloom.
And even then, it wasn't ready to use.
No. That bloom then had to be repeatedly heated and hammered by blacksmiths just to remove the impurities before it could even be shaped into a single rivet.
The metallurgical supply chain alone is staggering, but the textiles required for this fleet are almost beyond comprehension. Because the ships relied heavily on large, square sails, we are looking at a society that had to produce sails capable of catching the heavy winds of the North Atlantic without shredding.
Right, which takes a very specific material.
And these sails were primarily woven from sheep's wool. The sheer volume of raw material required is a mathematical nightmare. Producing a single large sail, say, for a 30-meter-long ship, required the raw wool from hundreds of adult sheep.
And harvesting the wool is just the initial step in a grueling, months-long manufacturing process. The wool had to be meticulously cleaned, sorted by fiber length, and then hand-spun into miles of durable yarn using simple drop spindles.
Which was incredibly time-consuming.
It was. And this task fell almost entirely to the women of the society. After spinning, the yarn had to be woven on heavy, upright, warp-weighted looms. It was an incredibly slow, physically demanding process that required immense skill to ensure the weave was tight enough to capture the wind and withstand the brutal exposure of a maritime environment.
And to make the wool truly effective as a sailcloth, they essentially had to waterproof it, often by smearing it with a mixture of animal fat and red ochre, which added weight and durability. The labor investment is astronomical. The creation of a single sail could take a skilled team of weavers over a year to complete. The sail was arguably more valuable and represented more man-hours of labor than the actual wooden hull of the ship itself. It completely reframes how we view this society.
Entire communities just dedicated to this one goal.
Exactly. Entire localized economies, vast agricultural estates, and countless thousands of individuals must have been entirely dedicated year-round to feeding this relentless shipbuilding machine.
And that industrial machine was highly sophisticated in its output, too. They weren't just mass-producing a monolithic fleet of identical raiding vessels. They recognized that different environments and different objectives required specialized engineering.
So there wasn't just one Viking ship.
Right. The Viking fleet was categorized into distinct classes of ships, each meticulously tailored for a specific function.
Which is a really important distinction to make, because when the average person hears the term Viking ship, a very specific, aggressive image immediately comes to mind. You picture the terrifying, hyper-narrow warship sitting incredibly low in the water, packed shoulder to shoulder with armed raiders, slicing through coastal fog with a massive, snarling wooden dragon head mounted on the prow.
And, those vessels absolutely existed, and they were devastatingly effective. Those are the longships, specifically classified as drakkar or snekja.
The same as dragon ships.
Exactly. The drakkar, literally translating to dragon ships, were the apex predators of the medieval ocean. They were engineered for pure speed, extreme maneuverability, and the rapid deployment of military force.
So they were specialized for war.
Yes. They were incredibly narrow relative to their length, maximizing hydrodynamic efficiency, and relied heavily on rowers to achieve explosive bursts of speed for ambush tactics or retreating against the wind.
They were basically the shock cavalry of the sea. And the psychological warfare aspect of their design is fascinating, because the carved dragon heads weren't just decorative flourishes. They were deliberately crafted to incite terror and project power.
Oh, for sure.
But there is a deeply nuanced spiritual detail from the forces about these figureheads that completely subverts the idea of the Vikings as mindless aggressors.
This is such an interesting point.
The sagas detail how the crews were legally and spiritually obligated to remove these terrifying dragon heads when they were approaching friendly shores or when they were returning to their home ports in Scandinavia.
Right. They unmounted them to avoid offending or frightening the landvættir.
The landvættir, the local invisible land spirits that the Norse believed inhabited the rocks, the forests, and the coastlines.
You couldn't upset the local spirits.
Exactly. If you approached a friendly harbor with a snarling monster on your prow, you risked driving away the protective spirits of the land, bringing misfortune to the community.
It's a very careful balance.
It highlights how deeply intertwined the mechanical reality of the ship was with their animistic spiritual worldview. The ship was a weapon, yes, but it was also a conscious participant in the spiritual ecosystem of their world.
That integration of practicality and belief is everywhere in their culture. But the longship, as iconic as it is, was not the most common vessel on the water.
Right.
If we look at the daily functioning reality of the Norse maritime economy, we actually see the carve.
The carve is a fascinating middle ground. These were significantly smaller and broader than the great longships, typically operating with 13 to 16 pairs of oars.
Like a versatile runabout.
Yeah. If the longship is a military transport aircraft, the carve is like a private helicopter. They were high-status vessels, often owned by individual wealthy chieftains or prominent families.
Used for local errands, basically.
Yeah, utilized for localized trade, rapid transport around the massive, intricate fjord systems, or deploying smaller retinues in localized conflicts.
But if we really want to understand the true global impact of the Norse expansion, if we want to understand how they managed to permanently settle Iceland, colonize the hostile environment of Greenland, and successfully navigate to the coast of North America centuries before Columbus, we have to look at the third and arguably most important class of ship.
A heavy lifter.
Exactly.
Yeah.
You cannot transport a viable colonial population, complete with livestock, timber, and months of provisions, across the freezing North Atlantic in an open, low-riding warship. For deep ocean logistics, you need the Nar.
The Nar, or the bus. These are the unsung heroes of the Viking Age. They are fundamentally different beasts from the longships. While a longship prioritizes a narrow beam and a shallow draft for speed and coastal access, the Nar prioritizes volume and survival.
It's all about capacity.
Right. They were significantly broader, much deeper in the belly, and possessed a much higher freeboard, meaning the sides of the hull rose much higher out of the water to prevent the massive swells of the deep ocean from swamping the cargo hold.
They were the massive container ships of the medieval world. And because of their width and depth, relying on oars for primary propulsion was hydrodynamically inefficient.
Too heavy to row.
Right. While they had a few oars for maneuvering in tight harbors, the Nar was almost entirely reliant on its massive square sail. And this was a critical design choice, Because you didn't need 50 rowers taking up space and consuming vast amounts of rations, the crew of a Nar was remarkably small.
So more room for cargo.
Exactly. This left an enormous volume of internal space available for pure cargo.
And the economic lifeblood of the empire flowed through the holds of these ships. A fully loaded Nar could haul upwards of 60 tons of cargo across open ocean.
60 tons in a wooden boat.
We are talking about a transcontinental logistics network transporting immense quantities of high-value goods. They moved precious walrus ivory harvested in the high Arctic, massive shipments of timber to deforested colonies like Iceland, tons of preserved grain and honey, luxury furs from the East, exotic spices, and vast quantities of silver dirhams flowing up the river systems from the Islamic world.
It was a truly global network.
It was. And, it must be acknowledged, a massive volume of human cargo in the form of enslaved people taken from across Europe. The Nar was the heavy, lumbering heartbeat of an economy that connected the frozen fjords of Norway to the bustling markets of the Mediterranean.
And the historical reality of North American exploration perfectly illustrates this point. When Leif Erikson undertook the unimaginably dangerous voyage to establish the settlement at Lanso Meadows in Newfoundland around the year 1000, he did not sail a dragon-headed warship.
No, he needed something that could survive the trip.
He purchased and commanded a Nar. It was the only piece of technology on the planet at the time capable of surviving the brutal wave mechanics of the North Atlantic while carrying the requisite payload of settlers, tools, and livestock needed to establish a foothold on a new continent.
And we aren't just speculating about the capabilities of these vessels based on saga literature or, vague historical accounts. We have undeniable physical proof. Because the ship was the ultimate symbol of wealth, status, and technological supremacy in Norse society, the absolute elite were occasionally buried inside them.
Which is a gift to archaeologists.
Oh, absolutely. These ship burials act as immaculate time capsules, preserving the engineering in startling detail.
The preservation is largely due to the specific geological conditions of the burial mounds. In places like Norway, ships were dragged ashore, the deceased were placed inside with immense hoards of grave goods, and the entire structure was buried under massive mounds of dense blue clay.
And the clay is the secret.
It is. This clay created a perfectly anaerobic, oxygen-free environment. Without oxygen, the aerobic bacteria that typically cause wood to rot cannot survive, leaving the timber essentially frozen in time for a millennium.
It's just incredible luck.
It is. And the Oseberg ship is perhaps the most visually stunning example of this.
Excavated in 1904, the Oseberg ship is a masterpiece. It dates back to around 820 CE. It is a substantial vessel, over 21 meters in length, but what immediately strikes you isn't its size. It is the breathtaking, obsessive level of artistry.
It's covered in carvings.
Yes. Almost every available surface of the prow and stern is covered in incredibly complex, deeply carved, interlacing animal motifs. This clearly wasn't a rugged utilitarian raider built to smash into foreign coastlines. This was a high-status luxury vessel, effectively a royal yacht designed to operate in the sheltered waters of the fjords.
And the context of the burial reveals profound details about the societal structure, too. The ship contained the remains of 2 women, surrounded by a staggering wealth of grave goods.
Right.
There were intricately carved wooden sledges, a highly decorated wooden cart, massive tapestries, and the remains of numerous sacrifice horses and dogs. The archaeological analysis of the wood actually suggests that the Oseberg ship wasn't built specifically for the funeral.
It had a life before the burial.
Yes, it had been an active sailing vessel for roughly 14 years before it was finally hauled ashore to serve its ultimate purpose as a grand, eternal tomb.
It perfectly encapsulates how the ship transcended mere transportation to become a deeply spiritual vessel for the afterlife. But if Oseberg represents the artistic pinnacle of the culture, the Gokstad ship, which was excavated in 1880, represents its rugged, terrifying seaworthiness.
The Gokstad is a totally different animal.
It really is. Dating to around 890 CE, the Gokstad is larger, nearly 24 meters long, and significantly wider and deeper. It is stripped of the delicate carvings of Oseberg. It is a pragmatic, heavy-duty machine engineered to survive the deep ocean.
And the physical condition of the Gokstad hull allowed marine archaeologists to dissect the clinker construction with mathematical precision.
They could really see how it worked.
Exactly. They could measure the exact flexibility of the riven oak, the precise spacing of the thousands of iron rivets, and the structural dynamics of the hull. And the engineering was so manifestly robust that in 1893, a team of Norwegians built an exact, full-scale replica of the Gokstad ship.
which is such a bold move.
It gets bolder. They didn't just put it in a museum. They sailed it across the Atlantic Ocean to the World's Columbian Exposition in Chicago.
All the way to Chicago.
Yes. They encountered massive violent storms, and the replica performed flawlessly. The flexible hull contorted and absorbed the wave energy exactly as the shipwrights had intended 1,000 years prior. It definitively proved the intercontinental capabilities of the design.
And then, jumping forward in the archaeological timeline to the 1960s, we have the Skaldelev ships in Denmark, which provide a completely different kind of historical snapshot.
The Skaldelev find is arguably the most informative cross-section of the working Norse fleet ever discovered.
Because it's not just one type of ship.
Right. Deep in the Roskilde Fjord, archaeologists found the remains of 5 completely different vessels. But these weren't high-status burials. These ships had been filled with stones and deliberately sunk around 1070 CE.
They were used to artificially block a deep, navigable channel in the fjord. Likely a desperate defensive measure by the local inhabitants to prevent an incoming fleet from reaching their city.
A physical barrier made of ships?
It's like uncovering a submerged 11th century parking lot. Because it wasn't a curated burial of a single elite vessel, the blockade utilized whatever ships were available.
So you get a real mix.
Exactly. The find includes a massive deep ocean Nar built in Norway, a specialized coastal trading vessel built in Denmark, a terrifying 30-meter-long Drakkar warship built in Ireland, a smaller local warship, and a simple coastal fishing boat.
It's a gold mine.
Having all these varied designs preserved together allowed researchers to directly compare the subtle, brilliant engineering variations that tailored each hull to its specific economic or military function.
Which brings us to the most compelling and dangerous aspect of understanding this history. We possess the physical wood, we have the precise measurements of the rivets, the metallurgical breakdowns of the bog iron, and the stunning visual evidence of the carvings. But analyzing dead, static wood on a climate-controlled museum floor has profound limitations. You can measure the flexibility of a plank, but you cannot measure the terror and the split-second decision-making required to navigate that plank through a winter storm.
You can't see how it actually feels on the water.
Precisely. To truly understand why the Norse were so successful, to comprehend the soul and the absolute reality of these machines, you have to put them back into the water.
You have to expose the design to the elements it was built to conquer. You have to feel the violent pitch and roll of the hull and listen to the oak groaning under thousands of pounds of pressure.
You have to live it.
And that visceral need for context leads us directly to the incredible, harrowing work of Greer Jarrett, which is documented brilliantly in our sources, like the New York Times report.
His work is just phenomenal.
It really is. Jarrett is a doctoral candidate in archaeology at Lund University in Sweden, and he recognized the inherent flaw in purely theoretical archaeology. He determined that studying static artifacts and translating medieval texts wasn't sufficient to understand the reality of Norse navigation.
You can't learn it from a book.
So over the course of 3 brutal years, he went to sea. He meticulously planned and executed 26 separate voyages along the highly complex, dangerous coast of the Scandinavian peninsula, logging nearly 1,500 nautical miles of practical data.
And the parameters of his experiment were strict. I mean, he did not sail in modern reinforced yachts with auxiliary diesel engines. He piloted, reconstructed, mendorically accurate, clinker-built wooden boats.
Just him in the wood.
And significantly, he deliberately avoided using massive 30-meter-long ship reconstructions. He chose a specific type of boat called a firing.
The choice of the firing is crucial to his research. These are much smaller vessels, roughly 30 feet long. They're completely open, square-rigged, clinker-built boats. He chose them because they represent the statistical reality of the Viking Age. If we only focus our attention on the massive elite longships, we get a highly skewed, sensationalized understanding of normal maritime life. The Fieringer were the utilitarian pickup trucks of the era.
The everyday boats.
Yeah, they were the boats utilized daily by the vast majority of the population, the fishermen pulling cod from the icy waters, the farmers transporting livestock between islands, and the local merchants running goods up the fjords.
By utilizing these everyday vessels, Jarrett was engaging in extreme experimental archaeology. He stripped away all modern maritime safety nets. He sailed without GPS, without digital compasses, and without weather radar.
That is terrifying.
He exposed himself and his crew to the raw, unfiltered violence of the North Sea in a historically accurate, open wooden shell. His goal was to reconstruct the authentic, lived experience of Norse navigation. And the reality they encountered was far removed from the romanticized sagas.
Oh, I bet.
It was a state of almost constant, terrifying chaos.
The accounts of his voyages, well, they read less like an academic paper and more like a survival thriller. Jarrett is not an amateur either. He has seawater in his blood.
Yeah.
His father actually sailed him through the Riving, which is the world's third largest tidal whirlpool located off the coast of Scotland, when he was only 18 months old.
Oh, wow. So he grew up on the water.
Exactly. So his baseline for maritime panic is incredibly high. But out on the open North Sea, attempting to manage a heavy square sail in a 30-foot open boat, the hazards they faced were relentless and frequently bizarre.
The primary threats were the massive, violent tidal currents that sweep through the archipelagos.
Right.
Those currents are capable of pulling an underpowered sailing vessel directly into submerged reefs, but they also faced highly unpredictable biological hazards.
Biological hazards.
Yeah, on one occasion they had a terrifyingly close encounter with a massive minke whale that took a profound amorous interest in their small wooden hull.
Amorous? Wait, really?
Yes, it actively interacted with the boat in a way that threatened to completely capsize them.
And is wild.
And on another voyage, a modern submarine suddenly breached the surface in dangerously close proximity to their tiny wooden vessel, violently displacing the water all around them.
That is the ultimate anachronism right there. But the mechanical failures provide the most profound insight into the resilience required by these crews. During one particularly chaotic encounter, a collision with another vessel resulted in a catastrophic failure. Their ship's yard snapped.
Which is a disaster.
A complete disaster. The yard is the massive, heavy horizontal wooden spar hoisted high up on the mast that supports the entire width of the square mainsail. If that spar breaks while you are navigating turbulent coastal waters, you lose all propulsion.
You are completely stuck.
You are dead in the water, entirely at the mercy of the current. But Jarrett's crew, which consisted of 2 men and 2 women, couldn't rely on a Coast Guard rescue. They executed an emergency mid-ocean repair by lashing the 2 broken halves of the thick wooden spar together and literally hammering them back into a functional unit using the heavy, blunt butt of an axe.
While on the water.
Mid-ocean. It is a stunning display of improvisational, high-stakes problem-solving that perfectly mirrors the grim reality of 9th century seafaring.
The physical endurance and mental fortitude required to operate in that environment is just staggering. But of all the hazards Jarrett documented over his 1,500 nautical miles, the most terrifying, the most lethal threat wasn't mechanical failure, and it wasn't marine life.
What was it?
If we connect this to the bigger picture, it was a highly localized, deeply violent meteorological phenomenon that the Norwegians refer to as fallvinder.
The physics of a fallvinder are terrifying. It translates roughly to falling winds, and it describes a specific type of adiabatic wind.
Right.
You have massive, high-altitude coastal mountains covered in freezing air. That dense, incredibly cold air suddenly cascades off the steep slopes, accelerating rapidly as it falls, and slams violently downward onto the surface of the water without any atmospheric warning.
They do not blow horizontally across the ocean like a standard storm front. They drop vertically off the topography.
Straight down.
Yes. The accounts note that these sudden localized downdrafts can reach speeds comparable to a minor tornado. They instantly whip the water into a chaotic frenzy and exert massive, unpredictable forces on a square sail.
Imagine standing in a 30-foot open wooden boat, balancing on a shifting, clinker-built deck, attempting to physically haul in a massive, heavy wool sail, when an invisible tornado made of freezing airdrops directly onto your head from the mountain right above you.
It's a nightmare scenario.
Surviving that requires a level of seamanship that borders on instinct. It completely shatters the simplified idea of how these people traveled. It proved that Norse navigation was not a matter of looking at a map, drawing a straight line from point A to point B, and passively riding the wind.
Not at all.
It was a constant, dynamic, highly dangerous negotiation with the environment.
And that dynamic reality is crucial. Researchers at the Viking Ship Museum, commenting on Jarrett's data, emphasize that a Norse captain didn't have a single route. They had to possess a deep, localized mental database of dozens of potential routes, hidden anchorages, and tidal patterns.
They had to know every inch of the water.
Right. They had to constantly read the texture of the water, anticipate the sudden shifts in weather based on the cloud formations over the mountains, and adapt instantly. But Jared's grueling physical voyages didn't merely confirm that sailing was difficult.
Right, they led to something bigger.
They led to a major, deeply surprising scientific plot twist that alters our fundamental understanding of the era.
And this is where the experimental archaeology violently collides with deep geology. Because as Jarrett was sailing these reconstructed vessels along the coast, he was meticulously cross-referencing his real-time position with medieval sailing accounts.
He was trying to follow their exact paths.
Right. He was attempting to locate the specific safe harbors, narrow channels, and vital anchorages detailed in the historical texts. But the physical reality of the landscape simply did not match the historical descriptions.
It didn't line up.
At all. He was sailing to coordinates the text described as deep, navigable channels, and finding them completely blocked by dry land or impassable shallows.
To solve this massive geographic discrepancy, Jarrett took the massive amount of practical sailing data he had accumulated and combined it with advanced digital elevation models of the Scandinavian landmass.
Right.
He was attempting to map the effects of a massive geological process known as isostatic rebound.
Isostatic rebound is a fascinating concept. During the last major ice age, the entirety of Scandinavia was buried under glaciers that were miles thick.
Massive sheets of ice.
Yeah, and the sheer, incomprehensible weight of that ice cap literally depressed the Earth's crust, pushing the landmass down into the mantle. When the climate warmed and the glaciers eventually melted and retreated, millions of tons of pressure were suddenly removed.
The weight was lifted.
Right. So the Earth's crust, which is somewhat elastic, began to slowly, inexorably rise back up, rebounding like a massive sponge returning to its original shape.
And that geological rebound is not ancient history. It is an ongoing process. The landmass of Scandinavia is still rising today.
Which is crazy to think about.
By utilizing his digital models, Jarrett mathematically stripped away the current elevation, effectively reversing the geological clock to determine exactly where the sea level sat during the Viking Age. And the results are staggering. He discovered that the land in certain key areas of Scandinavia has risen by as much as 20 feet over the last 1,000 years.
A 20-foot difference in sea level completely obliterates the modern map. It means that the intricate, dangerous coastlines the Vikings were actually navigating look profoundly different today.
Completely different.
Massive tracts of land that we currently perceive as dry, stable coastal farmland or low-lying peninsulas were entirely submerged beneath the ocean a millennium ago.
They were underwater.
Right. And conversely, deep-water harbors that we previously assumed the Norse utilized might have been geographically impossible to access, while narrow, hidden channels that look like dry ravines today were actually vital, navigable maritime highways.
It forces a complete reassessment of the geopolitical landscape. By adjusting his navigation models to account for this 20-foot shift in sea level, Jarrett made a groundbreaking discovery.
This is the best part.
He identified 4 completely unknown, entirely decentralized Viking maritime havens scattered across remote islands and previously ignored coastal features. These were not the massive, fortified trading towns mentioned in the major histories.
They weren't obvious ports.
No, they were informal, hidden anchorages that modern archaeology had entirely missed because they are now sitting high and dry.
And the existence of these hidden, decentralized havens fundamentally alters our understanding of how the Norse operated on a macro level. It definitively proves that they didn't just timidly hug the known coastline, hopping cautiously from one major established settlement to the next.
They were far more strategic.
They possessed the technology and the geographic knowledge to strike out into the open, dangerous sea, utilizing a vast, complex, and highly secretive network of these hidden staging posts.
This hidden infrastructure was the key to their global reach. It allowed a fleet of shallow-draft, clinker-built vessels to navigate safer, infinitely faster routes across massive distances.
They had their own secret highways.
Exactly. They could bypass hostile fleets, wait out the terrifying fall of winter storms in completely concealed anchorages, and extend their logistical reach far beyond what a conventional maritime culture could sustain. It is the hidden geological secret that explains how a decentralized society could efficiently move trade goods from the bustling markets of Baghdad, up the Russian river systems across the Baltic, out into the North Atlantic, and all the way to the old-growth forests of Canada.
It is a staggering realization. So let's try to pull all of these disparate threads together and look at the complete tapestry.
Sounds good.
We started our journey examining the microscopic cellular structure of a single oak tree growing on a windy hillside, and we've ended up mapping a massive hidden global trade network dictated by shifting geological forces.
Quite the journey.
Yeah, and when you analyze the Viking ship through this highly detailed, multidisciplinary lens, it completely sheds its reputation as a mere vehicle for barbaric violence. Yes, they were devastating raiders, and the violence was very real, but the ship itself is a profound marvel of human ingenuity and environmental adaptation.
It really is.
It is a masterclass in organic engineering that brilliantly prioritized dynamic flexibility over brute, rigid strength. It was the catalyst for an incredibly sophisticated early industrial complex that required the total mobilization of an entire society. From the blacksmiths smelting bog iron to the women spending years weaving wool sails.
Everyone was involved.
And ultimately, it was the supreme cultural bridge of its era, a piece of technology so perfect that it connected completely isolated worlds across impossible distances.
And that is exactly why the grueling, dangerous experimental archaeology conducted by people like Greer Jarrett is so absolutely vital to our historical understanding.
We need that practical context.
Exactly. By painstakingly building these clinker hulls the exact way they were constructed a millennium ago, using the exact same riven timber, and by deliberately sailing them into the exact same violent freezing storms, Jarrett and his crews are achieving something profound.
They're reliving it.
They are creating what he beautifully terms a bridge of experience. They aren't just passively reading historical texts in a library. They are physically enduring the exact same freezing winds, gripping the exact same style of tiller, and utilizing the exact same technological solutions to survive the exact same life or death scenarios as the Norsemen.
It's an incredible dedication to the truth.
They are effectively collapsing 1,000 years of history through the shared, undeniable physical reality of the sea.
The next time you encounter a piece of wood in your daily life, whether it's the polished surface of a dining table, the rough floorboards of an old house, or just the trunk of a tree in a local park, I want you to pause and consider the hidden microscopic strength woven into its grain.
The natural architecture.
Right. I want you to think about how the simple, brilliant realization that wood is infinitely stronger when you coax it apart along its natural fibers, rather than violently cutting across them with a saw. How that single piece of physical understanding provided the foundation for human beings to conquer the most violent, unforgiving oceans on the planet.
It is a perfect, elegant representation of the profound relationship between raw, natural materials and boundless human ambition.
It truly is. But before we conclude this deep dive, there is one final, incredibly dark detail from our sources that we want to leave you with.
Ah, yes, the cosmology.
Throughout this entire journey, we have rigorously analyzed the practical mechanical brilliance of these ships, the metallurgical properties of the rivets, the chemical composition of the tar, the hydrodynamic genius of the shallow draft. But to the Norse people, the ship was not merely a tool.
It was much more than that.
It was so central to their existence, so absolutely vital to their survival, their wealth, and their power, that it transcended mechanics and anchored their entire cosmology. Their religion, their foundational myths, their entire view of the universe was fundamentally maritime.
The sea permeated every aspect of their spirituality. Yorar, the god associated with the sea, seafaring, and immense wealth, was one of the most venerated deities in their pantheon. They didn't just sail on ships. As we saw with Oseberg, they utilized them as literal vessels to transport their dead to the afterlife.
But the mythology goes to a much darker, much more terrifying place than grand royal burials. The historical notes detail an aspect of Norse cosmology that is incredibly haunting.
It really is unsettling.
In their deeply complex belief system, the definitive end of the world is called Ragnarok. It is the twilight of the gods, the ultimate, inescapable, apocalyptic battle where the known world is utterly consumed by fire, water, and chaos. But in this mythology, the apocalypse does not arrive on a pale horse.
No, it doesn't.
It does not descend from the heavens, it arrives on a ship.
A monstrous mythical ship known as Naglfar.
Yes, Naglfar. And according to the deepest layers of the myth, Naglfar was not a masterpiece of engineering. It wasn't clinker built from dense riven oak cut from a windy hillside. It wasn't meticulously waterproofed with pine tar and sheep's wool.
It was something else entirely.
Naglfar, the ship vast enough to carry the legions of chaos to destroy the world, was said to be constructed entirely, piece by piece, out of the untrimmed fingernails of the dead.
Such a grotesque image.
It's deeply unsettling. But I want you to sit with that thought for a moment. I want you to imagine just how deeply a society must be tethered to the sea, how thoroughly and completely their entire existence, their economy, and their psychology must be defined by the temper and the crushing waves, for their ultimate world-ending nightmare to arrive not from the sky, not from the earth, but sailing toward them on a lapsed drake hull.
It is the absolute ultimate testament to the terrifying power of the ship within the human mind.
Something to ponder the next time you look out at the dark water of the ocean. Thanks for joining us on this deep dive. Heliox is produced by Michelle Brucker and Scott Bleakley. It features reviews of emerging research and ideas from leading thinkers, curated under their creative direction with AI assistance for voice, imagery, and composition. Systemic voices and illustrative images of people are representative tools, not depictions of specific individuals. Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other episodes, responding to the content, and checking out our related articles at helioxpodcast.substack.com.